Alright, so today y'all are going to be looking at some more complex versions of the free body diagrams and force problems. Just a kind of quick review of our steps is we're always going to start out with our free body diagrams. Then we're going to look and see, do we have any angles to break up? After we've done that, we're going to create our net force equations. And depending on what forces we have, we may have to do that in both the y direction as well as in the x direction. So remember, force is always equal to mass times acceleration. So when we're doing these net force equations, we're going to ask ourselves, are we accelerating vertically or horizontally? Both, neither. And once we've done all of that, then we're going to fall into our algebra. So that is our process. All right, so when we look at our first problem, we have a box on a ramp. In terms of looking at the pictures, I see these little crosshatches on the picture, so that's going to imply that we have some friction. Over here we've got a little paragraph that we can read, which also talks about friction. So we have a box of mass, it's moving up the ramp with an initial velocity. We have friction that's going to be working to slow it down. And we're going to try to identify the acceleration of the box. Okay. All right, so first things first, we need to draw our free body diagram. Okay. So free body diagram, we have our mass here, and what do we have? We have gravity pulling down, or force of weight. We have a normal force. A lot of people want to take and put the normal force going straight up to oppose gravity, but the definition of normal force is that it has to be perpendicular to the surface. So since my surface is going kind of at an angle, my normal force is going to be perpendicular to that at an angle. Our box was initially moving up the ramp, so opposing its motion is going to be our friction. So if it was moving up, then opposing that would be moving back, and that is going to be our friction. So here's our free body diagram, and that's what we got. So next up, we need to ask ourselves if we have anything that needs to be broken into angles, and we do have an angle down here, so not all of those things are perpendicular to each other. Okay. Essentially, at this point, I have two options. And one thing that people might think about is, well, I could take and turn my friction into two components. But then I'd also have to take and do the same thing with my normal force. I'd have to break it into components. And so that's going to be a little bit difficult. So something I might consider is if I thought about this picture, then I might think or recognize that two of those things are working off of each other. And so if I kind of imagine tilting or twisting my paper, then really this is the only one that's at a funky angle by comparison. So I really only need to break up that gravity. And so what I'm going to do is I'm going to essentially treat that gravity as a component that opposes the normal force and as a component that's moving down. Okay, so those are the two pieces of gravity that I'm going to try to break up and create. All right. For those of you who already know your trig and your geometry pretty well, you're going to get to be able to skip ahead here in just a second. For those of you who are less familiar with it, let's talk a little bit about triangles for a minute. Okay. So at the moment, we have essentially our ramp. We have gravity over here that's going straight down, and then we have our base. Okay. Over here is our angle. If I say that this angle was, let's say, 30 degrees, this is 90, and that means this would be 60, 30, 60, 90 triangle. Okay. And the reason I'm focusing on that is when we broke up that gravity with that orange arrow, I'm going to start to see that if this is 60, and now I've got this kind of perpendicular thing happening between the ramp and this component of gravity over to the side, okay, that's perpendicular. So what that tells me is that if that piece is 60, then this piece is 30. Okay? And what I'm trying to point out here is that whatever this angle is is also what this angle is according to geometry, always and forever. So what does that mean on my picture? Well, that means that whatever this angle theta is also this angle theta. Okay? So when I look at that, I'm going to ask myself, what is my opposite side? And what is my adjacent side? And essentially my gravity becomes that hypotenuse. So since this piece down here is my opposite, that means that I'm going to use the sine function. So this component would really be mg opposite or sine of theta. This side piece on over here would be mg adjacent or cosine theta. So those are my component pieces. Now I'm ready to, so I've done my free body diagram. I've broken up my angles. I'm going to start looking at my net force equations. Okay? So what am I going to treat as my y direction? What am I going to treat as my x direction? So in the y direction, my normal force is going to be a component of that. And then this piece of gravity will be another component of my y direction. In that same manner, this friction is going to be kind of like my x-axis, and this piece of gravity is also moving in that same axis, so it'll be part of my x-axis as well. So let's write some equations to describe what those forces actually are. Alright, so my net force in the y direction is equal to mass times acceleration. Is it accelerating in this direction? Is it leaving the ramp or falling into the ramp? The answer is no. So my acceleration is 0, meaning that there is no net force in the y direction. Okay? This tells me that my forces need to be balanced. Okay? So my normal force has to equal my gravitational force in that direction, or mg cosine theta. Let's talk about our x direction. So in the x direction, it was moving up the ramp. Friction's pulling it back, so it's going to be slowing down. So it's definitely going to have some amount of acceleration along this plane. Yeah, so it will have an acceleration. Okay? And so we know that that mass and acceleration has to be equal to some forces. Okay, what forces are acting in that x direction or that horizontal direction? Okay? Well, the friction is acting in that direction. Our friction is pulling us this way. I'm going to say that's a negative direction. And we have gravity down here pulling us in that same direction, okay, or in the negative direction as well. Okay. I could treat these both as positives. So just the fact that they're pointing in the same direction, we actually want to add our friction and gravity. So either both positive, both negative, but they need, if they're in the same direction, they need the same sign. I don't like negatives, so I'm going to go ahead and stick to the positive versions of them. Acceleration is going to be probably trying to slow us down. It's probably going to be working in the same direction. So by doing this and treating these two as positive, I'm going to probably be able to keep a positive answer, which is going to be kind of nice. All right, we have hit all of our physics. We drew our free body diagram. We broke up our angles. We came up with our net force in the y direction as well as our net force in the x direction. So really we've hit about as much physics as we have to hit. Yeah. There's one more level of physics that I can talk about, and that is the fact that I can break up this friction a little bit further. Yeah. When it comes to friction, when I think back to my question, it talks about a coefficient. Coefficient is mu. Yeah. So when we talk about friction, friction is based on our mu times our normal force. And when we're talking about static friction specifically, we usually say that that friction is less than or equal to mu times n. Okay? We write it as an inequality because that static friction could be a little bit, and it can, or it could be a lot. As long as it is less than what the normal force and that coefficient are doing, it's going to remain in place. Once I get over that hump, then it becomes kinetic friction, and we'll start to have that acceleration. Yeah. For our purposes, we're trying to find the point at which it's going to stop. So really, we're going to have that acceleration moving, and so we're only going to focus on when they are in fact equal. So I'm going to go ahead and I'm going to go back to my equation and I'm going to rewrite it, but I'm going to include, instead of F for friction, I'm going to use that mu and that N so that when we try to solve, we have all the components we need. So I'm going to go ahead and I'm going to bring down my mass and my acceleration, and I'm going to bring down my mg sine theta. So at this point, I have all the information I could possibly need, and it's going to come down to plugging in the numbers and actually solving it out. So let's grab a different color, and we'll do that. Okay. Mass. Okay. So they gave us our mass. They gave we're finding the acceleration. They gave us mu. We don't have N, normal force, do we? Oh, but we do have N. Okay. Remember when we wrote our equation earlier, we said that normal force is related to mg cosine theta. So we're bringing in those other facts, which is why even though we were focusing on the x direction, we still wrote the equation for the y directions in terms of those net forces, because they are going to build on each other. They're part of the same system as a whole. So I can expand that a little further. I've got my mass and acceleration is equal to my coefficient of friction times mg cosine theta plus mg sine theta. At this point, you can plug it in. If you want to save yourself a little bit of math, you'll see that we have m in every single term. So it's here, it's here, and it's here. So we can cancel it out if we choose. And effectively, we're dividing every term. When I get to a plus sign, a minus sign, a new mathematical symbol, we'd have to be able to get rid of that m and divide it out. So every term is being divided by m, which, simplifying our steps, is going to give us a equals mu times g times the cosine of theta plus g times the sine of theta. Again, we have all of these numbers. So my mu is going to be 0.3. We know gravity is 9.8 or 10. Cosine. Oh, I did not give y'all an angle. Let's make up an angle. Let's say our angle is 20 degrees. Yeah. Sorry about the fact that I left that off of your picture. And then not equals plus g times the sine of, again, that 20. I think I'm going to grab a smaller pen to make this easier to see. Alright, so we'll do a little bit of algebra, we'll plug that into our calculator, and we're going to get our acceleration. Alright, and so I'll let you finish out that problem. When you're done, make sure that you box in your answer. So acceleration is, and make sure that you're including your units. Alright. Okay. Our next question is going to build off of that same picture. Now we want to know how far, essentially what's our displacement, our delta x, up the ramp will the box move before it comes to a stop. Okay. So this is going to take us back to our Unit 1 information on kinematics. And it's important that we keep that fresh because those kinematic equations that you started with are really your foundation. They're not going to go away. Okay. So from that previous block of information, we knew that our mass was 3 kilograms. We knew that we had an initial velocity, or v naught, of 5 meters per second. We knew we had our coefficient of friction of 0.3. And we have our acceleration from the previous question. And then we want to find our delta x. Down here, if I keep reading, we want to find how far up the ramp the box will move before coming to a stop. So this tells us that our final velocity needs to equal 0. So looking at my kinematic equations, those big ones, I want to try to figure out what equation do I have that really uses my velocity to start and to finish, has my position or my displacement, and we also have that acceleration. So there's one equation that we can use that has all those components to it. That would be this equation here. So we're able to, again, we're going to know our final velocity. We know our initial velocity from the previous box. We know our acceleration from the previous question, and then you're going to be solving for this position. So that's going to be our final solve, and that's going to be what we're going to be looking for. So again, I'm going to let you do the math and check your work when we turn it in. And so what we're looking for here is delta x equals something in meters. All right, next question. We have a force of 2 newtons being applied to 2 blocks so that they stay in contact with each other. What is the acceleration of the 2 blocks? Okay. So, again, going to our steps. We're always going to start with free body diagram. So in this case, they're going to stay in contact, meaning we can treat them as one big system. Yeah. So you've got both blocks. They have a force being applied to them of that 2.0 newtons. We have gravity pulling down on our blocks, mass times the acceleration of gravity. And then we have a normal force pushing up. In this case, our normal force is going straight up because our surface is flat, and so if we're going perpendicular, we want that force to go straight up. We have no other forces acting vertically. I'm going to ask myself in terms of my net force equations. Yeah. So do we have any angles to break up? These are all perpendicular. So we have no angles, meaning we're going to move down to our net forces. Okay. We do have net forces in both the y direction and in the x direction. In the y direction, it's not rising, falling, changing. It started on the surface, it's staying on the surface. So we know that the acceleration in the y direction is 0, so our net force in the y direction is 0, meaning that this normal force going up has to balance our gravity going down. So let me grab a better color. Our normal force in the y direction has to equal 0. So our normal force going up minus our gravity pulling down has to equal 0, or our normal force has to equal our weight, our mass times gravity. In the x direction, we have a force, okay? And they tell us in the question that we can assume we have an acceleration. So we are going to have an acceleration, meaning our forces are not balanced, which makes sense because we have a force going forward, and we have nothing to balance it on this backside. Okay? So in the x direction, we have mass and acceleration, and that mass and acceleration is equal only to our 2 Newton force. Alright, which means that our acceleration is really our force of 2 newtons divided by the mass, okay? What mass is that 2 newtons moving? Well, that 2 newtons is actually moving both the 1 kilogram and the 2 kilogram. It's moving all 3 kilograms of mass. So when we solve, we want to use our total mass to answer this question. Essentially, if we're doing the net or the total force, then we want our total mass. Alright, so I'll let you do your algebra and solve. You should get an answer with our units, meters per second squared. So since we started out with a pretty tough one, we wanted to just pull back and show you something a little easy so that we're not always thinking about hard. We want to think about how we can simplify some of those steps as well. Alright, one more big one to look at, and then we'll go from there. Alright, for our bottom scenario, we have 2 blocks initially at rest and released at time 0. What is the speed of the box at time t equals 5 seconds? Okay. So We know their initial velocity is 0. We went from 0 seconds to 5 seconds, so our change in time is 5. And we want to know their final velocity. In order to solve this, we're going to need some more information. We're probably going to need to know our acceleration, because as I look at my kinematic equations, if I have two velocities in a time, I'm either going to be thinking about this equation on your formula chart, or it can be rewritten as this equation on our formula chart. So, in order to solve this question for my final velocity, I need to know my acceleration, which takes me back to Newton's laws and forces. So when we're talking about Newton's laws and forces, remembering our steps, we want to start with free body diagrams. And so this 3 kilogram mass. Well, if I have 3 kilograms here and 2 kilograms here, first I'm going to ask myself, what do I expect to happen? I expect this mass to accelerate down, and I expect this mass to accelerate up. So when it comes to my 3 kilogram mass, it's accelerating downward because of its weight, mass times gravity. It is being pulled backwards a little bit because of this other mass that it's attached to through my string or my tension. And you'll see that I drew this arrow much smaller than the other one because I want my gravity to win so that I can accelerate in that downward direction. On the other side, my 2 kilogram mass has its own weight trying to work against it, but we said it's going to accelerate up, meaning that upward force of tension has to be greater than the downward force of that 2 kilogram weight. When I look at these pictures, I do have two tensions. This tension comes from this string, and the tension on the other side comes from the same string. So those two tensions are the same, come from the same object, so they are the same value. I don't need to give them any subscripts. When I look at my masses, though, this left side is 3 kilograms. So it needs one mass, and the 2 kilograms is on the other side. It needs a different one. So I am going to need to keep track of the fact that this mass is not the same as this mass. So those subscripts become very handy. Okay. I can say that the tension over here and the tension over here are the same because they're part of that same rope system. Alright, so we've got our free body diagrams. Do we need to break up any angles? In this case, they're only going up and down, so we have no angles. So that means now we can skip to our next step of our net force equations. Okay, so net force. We don't need to think about anything in the x direction, just like we didn't have any angles, because they're only going vertically, so I'm only going to think about the y direction. Okay. It is accelerating, so we are going to keep that. We're actually going to make one of these equations for each side. So over on my left side, my net force is tension going up, gravity going down, and the acceleration going down. Okay. So tension going up, gravity going down, and the acceleration going down. On the right side, tension's going up, gravity's going down, and my acceleration is going up. These signs of positive and negative become really, really important, because when I think about my net force equation, I'm going to say that my tension going up minus my gravity on that first box going down has to equal my acceleration, which is negative over here on this side. Keeping track of that little 1, because this is the mass on my first side, or my left side. On my right side, tension's going up, gravity's weight force is pulling down, and my acceleration is directed upward, so I can keep that as a positive sign as well. I don't really need to put the positives that are implied, but just knowing that they're there. Alright, so now it's time for algebra. We're just going to see what can we solve, what can we simplify, what can we substitute into each other. When I'm looking at these equations, I can probably need to find some like terms. So the acceleration comes from those boxes pulling on each other. Okay, that acceleration is going to be the same. The tension comes from the rope, which is connecting those boxes, so it's going to be the same. So solving for one of them is going to help me. So I'm going to go ahead and I'm going to say, let's try to get rid of some of these positives and negatives. This tension is really equal to, let's add that other M1 and G to the other side. Okay, so over here it's gone. So now we have a positive M1G minus our acceleration. And over on this other side, let's add that M2 and G to the other side. And so our tension is M2A plus M2G. If you wrote it the other way, if you said M2G plus M2A, it's fine. Okay. What we do need to make sure is that we keep track of which things are positives and which things are negatives. So now we know that these are two tensions and that they're equal to each other. So algebra tells us that we can set these two equations equal to each other. So M1G minus M1A equals M2A plus M2G. Again, algebraically, at this point, again, all we're doing is algebra. So I'm going to try to figure out what is my next step. And algebraically, we usually try to combine like terms. So in terms of combining like terms, what are we looking at doing? So we are looking at, maybe we get our A's on one side and our G's on one side, so we group those. That way we're able to start canceling some stuff out and trying to solve for that A. So I'm going to add this one to the other side. Negative, positive, cancels out. And I can do this as a second step, or I can do it all at once. Okay. I can take this M2G away. So again, that side cancels out. So I have M1G minus M2G equals M1A plus M2A. All right. We do have the masses, we do have gravity, so at this point you could plug in. I'm going to kind of reinforce some of those algebraic practices because, as we saw in some of the previous questions, you're only writing expressions, and so sometimes they won't give us the numbers and we'll just have to get our math as simple as possible. So let's take a look at that. Okay. What I can do is, since G is in both terms, I could factor it out so that what I'm left with is M1 minus M2. Same thing over here. A is in both terms, so I could factor it out, and I'd be left with M1 plus M2. Ultimately, we were trying to solve for acceleration, which is a pretty common thing. So to get A totally by itself, I would need to divide that total mass, M1 and M2, off of this side. If I do it to the one side, I got to do it to the other side. And so this becomes kind of my standard form equation to describe the acceleration, is really G minus M1 minus M2 over M1 plus M2. And I have the information, I can kind of plug those in as I go. What this is really saying is that our acceleration is equal to force over mass. Well, the force comes from gravity trying to pull that first block down, but being balanced out by also having to pull that second block up. So it's gravity times the difference in those two, divided by that total mass. If those two blocks were exactly the same mass, if they were both 3, then it would just rest in place because neither one would be strong enough to pull it. If my box on the right was stronger, then it would pull it in that direction. So that's kind of what this equation ultimately tells us, is that the net, or the difference of those forces over the total mass, is what gives us our acceleration. Okay? Going back to my question, we need that acceleration. Once you have the A from down here, then I'm going to go ahead and I'm going to plug it in to either of those two equations. and get my final answer of my v. And with this problem, we didn't have the angles, so it simplified that step, but I did try to bring in the kinematics, which kind of steps it back up. So sometimes we'll have some nice, very basic questions, like the middle. Sometimes we'll have some ugly angles like the top. Sometimes we'll have a little bit simpler picture, but we can still end up with a process. So just trying to give you a range of what those problems might look like. Your very last question on this page builds off of these other concepts and ideas, and it is asking us to figure out how far the blocks will be displaced in this time interval. Okay. So at this point, you're going to know your acceleration. You have that initial velocity. You're going to have your final velocity. You're going to have your time. So you really have a lot of choices as to how you solve. When I look at my formula chart, I'm going to be drawn to two equations. I could be drawn to the one we used earlier with our final velocity squared is equal to v naught, the initial velocity squared, plus 2a delta x. Or I could be drawn to delta x equals the initial velocity times time plus 1/2 at squared. Both of these work and do the same, will get us to the same answer in the end. Yeah. I'm going to say that for me personally, I would probably lean towards this one for two reasons. One, delta x is already by itself, so I have less algebra to work. The second reason is this other equation over here really relies on our previous answer. So if I got this previous answer wrong, that's going to compound over time. Whereas in this other equation, this was already given to us in the sentence, given to us in the sentence, given to us in the sentence, and I was really only having to bring in that acceleration from before. But if I try to use the right side, there's multiple places I could have messed up leading up to that step, and so I may increase my chance of having a mistake there. Yeah. No matter which one you do, you should be able to get to a point of how far, or the change in distance, change in position, in meters. All right. Hope that helps, and we'll be working with some spring forces next week.